Okay.
So now we're going to see a simulation of a particle system implemented in
Squeak. Hello. Hello, everybody. We will talk about particle system. I don't know if talk in English or in Spanish. How many? What do you prefer? I prefer Spanish or French. That's more difficult.
We could do a mix.
Okay. Well, let's start in English. Let's try in English. We will talk about a particle system. Particle system is what you are seeing here in the screen. It is a way to make animations that are random animations, which are not defined, well defined at the beginning of the animations, and is, for example, to do animation of fire, of clouds, the winds, or the movements. For example, also for the hair, the hair, all that kind of animations that are not rigid, are not defined at the first step, so that this technique have some attributes for each particle. A particle could be anything like a pixel or an animation. For example, this is a circle. Could be anything. Here with the morphic, the implementation of this particular system is get much easier to implement. That's because the facilities that the morph have already implemented.
Our motivation to develop this particular system was that we developed gambling games, and so often we work with graphic designers and interact with them and resolve the problematics they give us are very rigid with static animations, with pre-rendered animations. So we need to develop a way to resolve different problematics with the system, with the particle system that could interact with environment variables and parameters. So we can have a way to show certain situations that are not pre-rendered and are very flexible and could interact with gaming parameters.
For example, I will try to explain which is the mechanisms that works that this uses to work. It has a system. For example, here with the halo, it is all the area where the particles are drawn. This square, it's called an emitter. I can have it. Well, this square, it's called an emitter. The emitter is the surface where the particles will start his life, and then depending on the parameters that are in the right side, that depends how they will behave, the particles. For example, here is resizing the emitter. So the first step is the generation, the creation of the particles. Also, that depends on the attributes they have and the position. Everything is random. Then the elimination or the remove of the particle, that depends also in the lifetime of each particle, and also is random. That is what all the randomly is what gives the life to these animations.
Please. What we mean with random is that the animations are all times fresh. It means this means that you don't have rigid animations, but flexible ones. So you can, as you can see, there are certain parameters as gap that changes some of the or touch some of the variables as the velocity, lifetime, color, position. All variables are touched by the gap percentage, so the animations are more realistic.
For example, I was touching some parameters. Here in this implementation, each particle is a morph. So this gives us a lot of flexibility for the animations, as this could be a circle or an animation morph. It could be anything. For example, we use it with an animation of a coin that is flying in the air, and that gives like it is a petrol pozo petrolero de dinero. That's example. Sorry for my English. Well, we can start talking about the attributes. The attributes we have. For example, the living particles. And also another parameter that is important in this to have nice animations is the time, because depending on what on the complexity of each particle, it is the time that the machine renders the whole animation. As in each moment, for example, in this case, there are living 50 particles. And each particle has its own life, and it is in each moment his attributes are modified, and all that calculation is in live. So if we have, for example, we have a lot of more particles, the animation will behave differently depending on the processing. The velocity. This is a vector of a velocity vector. The initial velocity vector. For example, where we can show the meter, for example, to show it. The surface of the meter can change also. For example, the mean particle size is the size that the particle will have when it starts its life, and the size it has when finished its life. The path, for example, this is an interesting thing. With this, it could be modulated something like a snow. Also, the particles don't need to be the same. In this case, we have the same, but it could be from different sizes or different shapes. We can use a bitmap or different bitmaps. That is the techniques that are used, for example, to do fire. For fire, there are 3 or 4 bitmaps that combined and getting randomly, they emulate a file, or also the explosion. For example, big explosions could be done with this. For example, the particle system was invented for a film that needs to have an explosion against a planet. And in that moment was coined this concept of particles. For example, here is the color of the particles. This is on time. For example, when the color when the particles start leaving. For example, when Martin start changing the color, change the color. The particles, the new particles have the new color. But that color, this could be done to change in the particle life also. I mean, the possibilities of animations are very large. For example, the fade in and fade out time. This is how the particles appears. For example, with a small fade in, they will be in transparent less time. This is the debugger. No, pon it. Don't worry, cambiar el cero. This is why it is in zero.
No, it's growing.
Bueno. Let's start again.
If you use PowerPoint, this will not happen.
Okay, this is what when working on graphic, we have a lot of time this kind of situation where if an error occurs in a particle, for example, this is multiplied by the amount of particles.
Un poquito cómo está armado.
Okay. Well, we can. Well, here it is again. Well, we can describe a bit how it is implemented. This, as I said, with Morphic, it is very simple to implement this. For example, this kind of animations. Obviously, these animations are not optimized in velocity. So if we have a lot of particles, it won't be very. It can have, for example, 500 of particles. But very easily could be done graphical optimizations to work with this. Also, it is planned to do with, but we plan to implement it with OpenGL to render the particles. Well, how does this work? Basically, it has a system morph that, in our case, is the whole. For example, all the area where are defined the particles, and it is also the area where the emitter will start running the new particles. The emitter, that it is this square, and each particle. And the other class is the particle system editor that is did not have any graphical functionality. Is only to manage the value of the attributes. In this implementation, the attributes are set not like functions, but it could be done like functions. The only function is the gravity. For example, if I get less gravity,
no zero. No zero, please.
No, it's zero. For example, a lot of gravity make the velocity to go down, and makes with acceleration that makes this field that they are floating.
A design decision was to build on morphs, or to make a model and then render only with morphs. But when we started to work with the first idea, that was to have the models on the one side and the morphs on the other side, we've seen that morphic gives all variables and parameters needed, and we need to replicate all and update once the updates are made. So we changed and worked on morphic. A particularity of this is that all objects use morphs. So you can have an emitter that is an ellipse, or circle, or a polygon, and a particle that is a star or animation or whatever. And the particle system could be also a morph. And all changes are implemented on the step method. So we have in very few methods the whole system implemented. Obviously, this is not final, and we are working. We are still working on that, and we have many ideas to get better the system and to allow the designers to interact with the editor. That this is very few functions have now, but the idea is that to give the editor to the designers. They work with the editor and have a particular system running, and then serialize, save the parameters used, and load it into the games.
Yes, here I was touching some parameters. Well, I'm following with the implementation. What we this word is like with the morphic. For example, there are all the parameters are the getters and setters of the meter, and everything is condensed in the span method that gives the values and creates the needed particles and gives the initial values. Then the particle in his steps in each step where I have a class. In each step it modifies its attributes. Also, with the morph, the flexibility with the morph is that we also can have two emitters, for example. We didn't implement this yet, but we could have two emitters, different kind of particles. The morph gives a very good interaction. Well, I don't know. ¿Tenemos algo más? Well, I think that we did a review of this system. I would like you to make us a question, and so we can explain anything that you interest. I don't know if it is interesting to show how it is implemented in deep, but if you want, we can get in this matter. For example, one thing that it could be very good to do for this is, for example, to have a centralized way to modify the value, the value of the parameters. So we can just get a constant value or any kind of functions, and with a centralized way. This is now done by adds and subtracts only. Only the gravity is a function, but we can. This will be a very good improvement. Also to manage in another way to improve the editor.
A question. Two questions. First one is where random behavior intervenes here. So you have parameters with values. What kind of randomness you add to those parameters and where? The
random parameters, for example, is where the place where they are born. The particles are born. For example, let's stop this. For example, where are they born inside this? It's random.
Okay.
And in general, all variables are affected by the gap. The gap is a percentage that modifies the initial value of a particle plus or subtract, and in that range are random. So, see, if we add a gap of 15%, this is that the value will be modified, will be calculated a range plus and subtracting that 15%, and a random hits there.
Okay. The second thing is, because the effect you get is visual, but have you thought on ways to measure outcome, the result, like, I don't know, how many particles end up hitting that part of the surface? Because
with collisions is
collisions, I don't know, some outcome, some result.
We don't have these measures. Only the lifetime of a particle is affected by a collision. It's only dies, but
no. For example, when in particular system, what they recommend, we didn't implement collisions. It could be implemented. Also, could be, for example, for surfaces or for walls to take a wall, or to take into account another objects that are not this particular animation. But the collisions in particular for the particles in general are not implemented because they are very expensive computationally between particles, not with other objects. And what they say is that also didn't give a measure more quality to the animation. It don't result in something in more quality for the animation. That's are the theoretical reasons for the collisions between the particles. Also, everything depends, for example, when in the amount of particles, on how the way they are rendered, the way the way they are rendered, and how much time do we have to render each particle. For example, I have found some example in videos for internet that they have a million of particles living in a moment. I don't know.
We just have within and the system. We use the principle first runs, then improve. We are just making it run. There are a lot of improvements and refactorings. This is we did this to solve a specific problem, and we have this now.
Did you think about implementing screens or some sort of attraction between particles?
Instructions.
Between particles.
Yes. Yes, we have, for example, another one thing that could be implemented. Yes, one thing we were thinking to implement is, for example, we have this. Let's do it a bit smaller. For example, here we thought to, for example, to do the particles here have the start direction is defined by this 1 and 13, but it could be done with the, for example, the derivative of the meter in the position. For example, the position now and the position in 10-20 milliseconds after. So we can have the velocity vector in that way. So the effect of that could be to throw
a wheel.
Like a wheel, yes, like a wheel. Also, the attraction between particles, it could be done. I don't know if it could be expensive computationally, because you need to know where the other particles, if they are near or not, and how much they affect. But I think it is not so, because the more complex the more expensive for the computer is not the calculations of the value, the next value, for example, but the expensive is to draw the particles. That is the more expensive for this. But yes, this could be done. What have this kind of system is that they are very flexible to do anything you need. For example, to do this wall like with bricks, it could be done like with a particle system. For example, running and having a snapshot of the run. For example, the hair of an animal or any kind of hair could be done like that. It runs, creates, the particles don't remove, but stay in its position, and they make the surface and the regular surface. Also could be done like I don't know how to say like a light pointing to some way, and the particles can change its color or be reflecting that light. This system is also used in the gaming industry. In the gaming, for example, for not gambling, the games in general. because in 3 dimensions. So that also is a bit more complex to draw, but they use it in this way. Also, when it was developed, this system, it was done in 3D for a film.
Okay, I think we are out of time. So
Okay.
thank you.